S is an empty set, you get permutations. If S is a set, you get derangements. But this was already very hard for humans. There was a famous problem in the 19th century called Problème de ménage. Of course, it took place in France. You had n married couples, Monsieur and Madame 1, Monsieur and Madame 2, and so on. And you want to make an interesting dinner party. So you want to sit, let's call 1 and 1 prime, Madame 1 and Monsieur 1 prime, 2 and 2 prime. Along a circular dinner table, and you want to make it interesting. You talk to your wife all the time. You already know anything about your wife, and vice versa. Your wife is tired of you. So you want to have somebody. So in how many ways can you sit something that men and women alternate, and no man, no husband sit next to his wife? So this is essentially. So first you see the ladies in some order, arbitrary order, and then you have to put the men. So that's circular. So here we have an extra condition, the beginning and the end. So it's basically, essentially this thing with circular condition. And for this, it was open for quite a while. And the people who solved it were a politician, a son, and an artillery colonel. And it's mentioned in by Luca, in a classic book, Theory of Number, by Edward Luca. He's a Martin Gardner of 19th century, but he was a professional, a number theorist, very smart guy. So he mentioned a solution. And the solution was, instead of this recurrence, you have something similar, but slightly more complicated. Instead of a second order recurrence, you have a third order recurrence. So it's Monsieur le Colonel Lesant. He was also a professional mathematician, but mainly a politician. He made to Wikipedia because he was a politician. And the colonel was Moreau. Monsieur le Colonel Moreau. He was a decorated soldier, a very good soldier, colonel, artillery colonel. Trained as an engineer, so he had technical training. In France, usually to be an officer, you have to have an engineering degree. But unfortunately, and he was very good amateur mathematician, but because of Wikipedia, unfortunately, he's done in history, most famous as the worst chess player who ever participated in an official tournament. In the Monte Carlo tournament, he was also an organizer, and he placed last. Everybody beat him. He didn't get through. So it's very unfortunate, but I shouldn't be talking. I'm sure he beat me in the game of chess. That I won't go to a tournament. So he was very brave, even though he was not such a good chess player. So I admire him. Anyway, in my book, the recurrence that he did was a very nice one. So both the son independently and the colonel, Monsieur le Colonel, and Moreau had the following answer. Call it A sub n again. So it's n. And you can easily write a computer program that in 1 second or in a few seconds can crank out the first 1,000 terms. At least the first, and the number gets bigger, so maybe the first few hundred terms. And then you submit it to the OIS. And that's a beautiful answer in the sense of Wilf. This is a perfect answer. It's a polynomial algorithm. But stupid humans, they don't like recurrences. Recurrences have a bad name. And one of my greatest heroes, Giancarlo Rota, in the seminal paper said that the first satisfactory answer was given much later. This was given in the 19th century by Touchard, by 20th century mathematician. And Touchard's formula was this one. It's a sigma. So for some reason humans, most humans, at least in the 20th century, hopefully no longer in the 21st century, because now we know better. So here was an explicit quote-unquote formula of Touchard. Why is this better than this? The complexity, at first you have to sum up n terms. And then you have to do, so to compile a table of the first 300 things, the computer will take a few minutes, and this will take a few seconds. This is much more preferable. The first few values you can do by hand. It's very easy. And then you can crank out, write option remember in Maple, and do it. And this is much more cumbersome. In fact, with the so-called Zalberger algorithm, you can go back. Suppose you only knew Touchard thing. So Touchard was not a complete waste. If Moreau and Dessalles would not have come this on purely combinatorial reasoning, you could have used Touchard to get this. If you go to Maple and use a command called Zalberger, in no time we get from here to here. So once you have a normal coefficient sum, you can get a recurrence. And a recurrence, as far as computations and other reasons, is much preferable. So this was already, for humans, a big tour de force with 0, 1. But why stop here? So very courageous, smart and courageous colleague of Niels Sloan at Bell Labs, at the legendary Bell Labs. Right now, unfortunately, Bell Labs is no longer a danger, is extinct. But in the good old days, John Riordan was one of the greatest combinatorialists, maybe the greatest of his generation. He tackled this. And he took 30 pages of hand calculations to get a formula for this, which I'll spare you. And Niels Sloan did a very good service to history. He scanned the memorandum and posted it on the website of the OIS. So anybody who wants to see human-generated mathematics from 1960s, really amazing to it. And this was circa 1963. And in 1977 or 78, roughly, a mathematician who is still alive, hopefully, at the University of Pittsburgh, Glenn Whitehead, did this. And the paper was even more complicated. But that's as far as humans went. And then I took the idea behind it. The beautiful human theory of root polynomials. I don't have time to tell you what it is. But Riordan developed based on previous ideas, but he solidified and had an idea, a beautiful theory of root polynomials. Basically, you call the restrictions in a chessboard. So the derailment one means you cannot do this. So you look at the restrictions. So it's really like placing the hooks. Really, you apply inclusion exclusion, and then when you apply inclusion exclusion, it's really placing hooks here. So that was easy. But if you have a more complicated board, then it gets more complicated placing. So you have, never mind the details, a whole theory of root polynomials, and I used the ideas in the theory, and I taught it to my computer. And once my computer learned how to do it can do it not like for one specific set at a time, like for 0, 0, 1, and 0, 1, 2, like people had a paper and worked the whole year for one set at a time. In one stroke, you had an algorithm that for any set S, it'll crank out the generating function, very complicated, recurrent, very complicated, but not for a computer. And after you do, it took this, to be honest, for big S, takes sometimes a few minutes. And if S is really big, a few hours. But once you have the formula once for all, to submit the first 300 terms to Sloan, or to first 1,000 terms, but Sloan only like 30 or 25, but then he has this, it's a few seconds. So you had, implicitly, and it's humanly readable. If you look at my website, every one of my papers, and Solot's paper, have 100 papers, computer generated. In the old days, in principle, would have been publishable. Probably would be rejected, but no referee would be willing to read and check all the details. But in principle, you can do it. But here is the bad news. Computers are much superior to humans, but only by a few orders of magnitude. So by hand did it for 0, 1, 2, and 3. Now my computer did it for 0, 1, 2, 3, and 4. Took it about 10 minutes. Took about 2 hours. It could have probably finished in a few days, but I had mercy on the computer, so I finished it. So for any subset S of 0, 1, 2, 3, 4, 6, a computer can do it using the algorithm. But if you replace S by some subset 0, 1, 3, okay, let's do all the prime. Okay. 2, 3, 5. I'm just making up an example. 7, 11. Question. How many permutations are there of size n such that the difference between pi I and I is not a prime number less than 100? No computer in the whole wide world ever, in my humble opinion, will be able to do it. So many problems. So the gap between the doable and trivial and the most probably undoable is very, very tiny. So we are like acrobats. We're going on a very thin line between, if we go on one side, we go to the trivial. If we go on the other side, we go to the impossible. So we're straddling a very, very thin line, an abyss between both sides. And our predicament is to make it as interesting as possible. Not impossible, but still something that you can do. So here's another example of this dichotomy. Also, a more recent paper of mine tells you how trivial humans are, but computers are not much better. Only a few orders of magnitude better. So, one of my favorite subjects is pattern avoiding permutations. And Brian Nakamura gave a talk about it in the seminar. Pattern avoiding permutations. Let me explain. Once again here, it's so easy to get from the utterly trivial, the moderately trivial, the semi-trivial, and the impossible. So once again, permutations, that's a universal set. But then the restriction is no longer like here, where the difference is avoided, there is no pattern. So, for example, if you have here 5, 2, 5, 3, and 2. That's a pattern. That's a CBA pattern. When you have some entry bigger, not next to it, possibly next to it, but usually not. Questions. How many permutations are there of length n such that you don't have the pattern CBA? Obviously, it's the same thing with ABC, it's a reverse it, and it's a nice, beautiful closed form formula. Not completely trivial in the human sense, but a nice exercise. It's the famous Catalan numbers. The Catalan numbers are known to count 200, at least 200 different families. And Richard Stanley has a website listing many of them. And people, humans like coincidences. Humans love, ooh, how nice it is, how amazing that the number of such things equals the number of binary trees with n leaves. And it's equal to the number of parentheses. But I'm not so impressed. The reason that the Catalan numbers come up so frequently is Zipf's law. The word in and it and I come up very often. But the word, I don't know, Constantinople or Timbuktu are much more rarer. This is a very simple sequence. It satisfies a very simple recurrence. And non-linear recurrence, also linear, So one way of defining the so-called Catalan numbers, and that's how, by the way, you can prove this. That's one way. And it looks complicated to the non-expert. But if you go to so-called generating function, the whole thing's called, every sequence can be coded in terms of, and stupid people say, worry about convergence and say it's a function, generating function, but the generating function is neither generating nor a function. It's a weight enumerator, and you can think of it as formal power series. And this, the current is equivalent to this algebraic equation. It's the simplest quadratic equation you can come up. Of course, the generating function for 2 to the power n also satisfies the equation. 1 minus 2x. So this is, it satisfies also an algebraic equation of degree 1. That's why it's a rational function. And the segment to the power n also comes up below. So that's the simplest possible non-trivial, non-degenerate generating function quadratic. Because it's the simplest, obviously it comes up a lot in many contexts, because we humans only detect simple things. So I'm not so excited about something new being Catalan. It's probably because it's not so complicated and it has the structure that is given by this. So recently there was a paper by otherwise smart mathematician Miklos Bona, combinatorics, University of Florida. That is completely paper and pencil. And he found the following thing. So look at all the 1, 3, 2 avoiding permutations. And then looks how many times a pattern 1, 2, 3 showed up. So you look, once you look at the set of 1, 3, 2 avoiding, you count how many times you have 1, 2, 3. So the number of 1, 2, 3 will show up. And you add them up. So you have number 1, 2, 3 to 5. So what he did, he found this amazing to him. So if you took another pattern and do it, you get the same sequence. Wow, what a coincidence. But once again, it's a very simple sequence. And once you taught it to my computer, I brought a brand new paper, and it found zillions and zillions and zillions of such coincidences. And once you teach it to the computer in 0.11 seconds reproduced the first half human-generated paper of Bona that probably took him a couple of weeks to do by hand. And not only that, it continued and did it for much more complicated patterns. So once again, once you have an idea, humans are still necessary. But don't waste your time on proving special cases. Once you have an idea, teach it to the computer. And then a computer can do, of course it takes time to program. Still today, humans needed to be programmed. But once the computer knows how to do it, it can do it so much faster than you. And not only that, contribute to Sloan many, many more sequences. And this, in my humble opinion, is the future of enumeration. You still need an ingenuity. And unfortunately, most people who are not familiar with computers look down on computers. Well, because for them it's just computing, it's just routine computation. And it's such a shocking thing. Brilliant people who did, for example, computational number theory, that is at least as challenging, and in my opinion, much more challenging than paper and pencil number theory, have trouble getting jobs, have trouble getting tenure. I won't mention any names, but it's really, really shocking, because we still are backwards. In the beginning, in the second decade of the 21st century, we're still behind. So we have to get rid of this mentality. No offense, Professor Ivanich, But if you would have learned how to program, you are genius. I agree that you are genius. But you're wasting your time. Take a few months, go to my course, learn how to program, and then use your ingenuity and teach all your tricks to the computer. Program them, and then you can get everything you did so far much faster, and lots of new stuff too. So this is my advice to young men, especially young people, young men and women, and also old men and women. It's never too late to start a computer. And then we conclude with another gap. This is my favorite. Counting lattice animals. That so far, people using many hours of computer time only got 56 terms. So what can be simpler than this? So you look at the grid, and you look at the collection of lattice points that are connected. And anyway, in how many ways, what the exact number of ways of placing n dots on the two-dimensional square lattice such that, and let's fix this to be the origin, that they are continuous. There's no gap. You can always walk from every place to any other place. Nobody has any clue, and I'm willing to bet that in 100 years nobody would know A of 1,000. Probably it's intractable. Proving it's intractable is also intractable. So in 1,000 years we would not know that A of 1,000, and probably will not know to prove that we never know, but prove formally, rigorously. But if instead of having this, you add the condition that from the origin you can always walk from one place, from one dot to the other, only using right and up steps, not going backward, then it's called directed animals. And for this is a beautiful closed form, almost closed form. And this you can easily find A1000 in a few seconds. So that's tweaking the conditions a little bit. Make it from intractable problem to doable problem. Not completely trivial, but doable. So this is the sad part. The Zeiberger dichotomy is trivial, at least for computers, or impossible. But maybe there is a measure zero set of problems that are in between, the delicate cut, and we have to concentrate on this, and if possible also prove intractability. By proving intractability, unfortunately also may be intractable. So that's life. Thank you very much.
Is there anyone with questions? Okay, let's finish the question.
Thank you.